Hello, everybody. My name is Barbu Revencu, and I'm a PhD student working with Gergely Cibra at Central European University in Budapest. Today, I'm going to present you a set of studies meant to investigate infants' understanding of animations. Let us start from the very commonplace observation that in addition to the use of mental representations in cognition, we use external representations abundantly in communication. We use maps to represent space, calendars to represent time, numerals for number, and language for virtually anything we can think of. Now, representations can carry and thus convey information about at least two types of content. On the one hand, representations can carry information about particular states of affairs. Here is a definite description, for instance, this talk referring to what you are now listening to. Or here is an old map of Toronto, the particular city where we were supposed to be right now. And here is a caricature depicting the former president of the US, an actual individual. On the other hand, representations can convey information about fictional or non-specific entities too. So if I ask you, for example, to imagine 20 tosses of a fair coin, you won't conjure up an image of a specific coin. Rather, you will use your coin concept to generate a novel token that will not pick out any coin in the world. Or take the map of Hogwarts, the wizarding school attended by Harry Potter and colleagues, which has no counterpart in the real world. And finally, consider this Heider-Zimmer-like still depicting a few agents interacting inside a house. Mind you, these are not particular agents, nor is this a particular house. As far as I know, most developmental research, as well as most philosophical thought, have focused almost exclusively on the first category to the extent that representational understanding has been equated with representations of particulars in the world. There is, however, one type of representation which is typically not oriented towards particular objects or states of affairs in the world, namely animations, which are pervasively used in developmental research. And by using animated stimuli, we have learned in the past 30 years that infants are able to draw various inferences based on them, ascribing agency to chasing balls, beliefs to flatfish, and dispositions to geometric shapes. Little is known, however, about what infants make of these stimuli once they start interpreting what is going on. Do they, for instance, take these figures to be real agents engaged in actions that are occurring here and now in front of them, or do they know that these are representations just as adults would? As a first step towards tackling this question, we outline four possibilities for infants' interpretation of animations. First, infants might not understand animations at all. This is unlikely given how many studies have used this methodology, but nonetheless possible. Second, infants might think that animations are real, happening in the here and now, and spatiotemporally continuous with the surrounding environment of the screen. Third, infants might think that animations are real and happening in the here and now, although not continuous with the surrounding environment, just like boxes or aquaria. And fourth, infants might treat these stimuli as representations, though not necessarily as representations of particular states of affairs. In the remainder of this talk, I'll present our first experimental steps towards figuring out what 19-month-olds make of animations, construed as a broad stimulus category. To do this, we designed three experiments that combined reality and animation in different ways. First, we got a baseline for a simple task where everything was real. The question was whether infants are able to track a ball that falls from a seesaw to the left or to the right in one of two boxes. We predicted in this baseline experiment that when infants choose, they would choose the box correctly. That is, they will choose the box that was on the same side as the falling event. Here, this would be the orange one. Second, we asked what happens when infants are confronted with a crossover situation. When they see a ball falling on the screen, will infants expect to find it in boxes underneath the screen? For this experiment, we predicted that infants would make fewer box choices when asked where the ball is, and that there would be a chance when choosing a box. Finally, we asked if infants are able to track where an animated ball is falling if everything is on screen, predicting that infants will pass this version of the task. When choosing a box, they will choose based on the falling event just witnessed. Based on pilot data, we tested 16 19-month-old babies in each of the 3 experiments. And each of the 3 experiments started with the same warm-up phase in which an experimenter dropped a toy in one of the 2 boxes, pushed them towards the infant, and asked them, where is the toy? Once infants passed 2 consecutive trials in a row, the test phase began. In experiments 1 and 2, the 2 real boxes were moved after familiarization under the seesaw or the screen, whereas in experiment 3, they were removed from the table. Across 4 test trials, infants saw a real or an animated red ball fall to the left or to the right of a seesaw. The experimenter then pushed the boxes towards the infants and asked them, where is the ball? Of course, in experiment 3, there was no pushing because everything happened on screen. After each trial, infants were congratulated regardless of what they did and were offered one of the 2 toys from warm-up, meaning that infants didn't get any feedback on the ball location. The location alternation across warm-up and test was ABBA for all infants, where A and B stand for left and right respectively. Where a particular infant got their first warm-up trial, left or right, was counterbalanced across subjects. We coded 2 primary dependent measures on each trial. First, whether infants made a choice or not, and second, if a choice was made, whether that choice was correct or incorrect, or by correctness, I mean choosing the box that was on the same side as the falling event. For reasons that will become clear in a minute, we also coded whether the infants point to the center of the seesaw or screen instead of choosing a box. Moving on to the results. Here are the results on infants choosing a box when asked where the ball is. The question we are interested in is whether the 3 setups differ in how likely they are to elicit a box choice. What you can see on the graph is the proportion of infants' choices across the 4 trials. Remember, in each trial, infants who pointed to one of the 2 boxes got a score of 1 and 0 if they didn't. We averaged these scores across the 4 trials and got a value between 0 and 1 for each infant. These are the individual dots that you see on the graph, on top of which you can see the box plots corresponding to the 3 distributions. Experiment 1, the reality baseline experiment, elicited the highest proportion of choices in stark contrast to experiment 2, whose median is much lower, and with experiment 3 being somewhere in between. Because the distribution of the proportion of choices across trials was not normally distributed, we ran the non-parametric equivalent of an ANOVA and found that the distributions underlying box choices are not the same. Pairwise comparisons reveal that this difference stems primarily from the contrast between reality and the crossover experiments. However, it was not the case that infants were less likely to provide a response to the question, where is the ball, across the 3 experiments. If we take into account the secondary measure I have mentioned, the difference goes away. Infants in the crossover experiment choose to point to the screen instead of the 2 boxes, even though the boxes were made salient by the experimenter who pushed them towards the infant before asking where the ball is. This strengthens the interpretation that they did not think that the animated ball could have landed in the boxes below the screen. As for accuracy, we were again interested in whether the 3 setups differ in how likely they are to elicit accurate responses. In other words, do infants take the falling event into account when choosing a box? For each trial in which infants chose one of the 2 boxes, they received a score of 1 if they chose the box that was on the same side as the falling event, and 0 if they chose the other one. As with choices, for each infant, we computed the average over the plus choice trials. And as you can see on the graph, in experiments 1 and 3, when everything was either fully real or fully animated, infants were close to ceiling, but they were perfectly a chance in experiment 2 when faced with a hybrid of animation and reality. Statistical tests confirm what you can see on the graph. There is no difference between experiment 1 and 3, but both differ from experiment 2. In order to take into account both choice rate and accuracy rate simultaneously, we built a hierarchical Bayesian model to address the following question. After seeing a ball falling left or right, Do infants believe it is in the box on that side? The inferential problem is as follows. There are three different setups: reality, crossover, and animation. And for each ball falling event, infants can either come to believe that the ball is in the box or not entertain this belief. What we observe, however, is whether infants make a choice or not, and if they do, whether the choice is correct or incorrect. And we want to use that behavior as a proxy for their beliefs. The assumptions underlying the model are as follows. We start from an identical uniform prior on infants' beliefs. In other words, the model makes no assumptions as to whether infants would be more likely to be on the left or on the right side of the tree before seeing any data. We do assume, however, that infants are more likely to make a choice if they think there's a ball in the box and more likely to choose correctly. We also assume that infants are roughly equally likely to choose a box or to refrain from choosing one if they don't entertain the belief with the content ball in box, and that they choose a box at random if they do so. We feed the observed data into the model and thus invert it to get one value for each of the three experiments. That value, call it small b, for belief, will be between 0 and 1, and will tell us how likely it is that infants are on the left or on the right side of the tree in each of the three experiments. Values close to 1 indicate that infants believe that there is a ball in the box, while values close to 0 correspond to the opposite. Here are the estimates on little b for each of the three experiments. As you can see, the Bayesian model agrees with the separate frequentist analysis in that it outputs posterior distributions that peak around 1 for experiments 1 and 3, while peaking around 0 in the case of the crossover experiment. When we perform a pairwise comparison among the three experiments, we find that experiments 1 and 3 did not differ from one another. This is the green histogram in the middle, showing that the posterior of differences peaks around the null value, which is 0, while the left and right red histograms representing comparisons between the crossover experiment and the other two exclude 0 as a plausible value, suggesting again that the crossover experiment is the odd one out, the one in which infants didn't form the belief, aha, the ball landed in the box. In sum, we started off with 4 hypotheses about infants' understanding of animations. First, animations might be incomprehensible for young infants. Second, animations might be interpreted as fully real. Third, animations might be taken as real, but not as spatiotemporally continuous with the surrounding environment. And finally, animations might be treated as representations. Our findings so far show that for 19-month-olds, the environment is not a continuous spatiotemporal soup. They can distinguish animation from reality and hence are not naive realists. Namely, they do not expect animated balls to fall off the screen, which allows us to rule out hypothesis 2. And they can, however, track the location of real balls falling off a seesaw, as well as the trajectories of animated balls within the confines of the screen, which allows us to rule out hypothesis 1. The next logical step is to continue the elimination process, look into hypothesis 3, and ask whether infants have simply learned the rule according to which screens have borders which do not allow objects to pass through, a possibility that is compatible with the data from the first 3 experiments. We are currently investigating just that. Before ending, allow me to thank our colleagues Dori and Yuli for data collection and coding, Denis and Laura for theoretical discussions, Adam for Bayesian guidance, and CEU and the European Research Council for funding me and this project. Do not hesitate to get in touch should you have further questions, suggestions, criticisms, or any other feedback that you think might brighten my day. Thank you.